Let's come back to the problem of approximating an area under a graph. So remember, the situation is we have some function, f of x, and we have a couple x values, a and b, and we want to find some nice sort of mechanical way of expressing an approximation for the area under this graph. And we've sort of given up on finding the area exactly, so really we just want an approximation, some nice way to approximate the area. Well, to approximate an area, we're going to have to use a shape that we already know the area of. And there are only a few shapes that we know the area of: rectangles, triangles, circles, maybe trapezoids, I guess, but those are really rectangles with triangles stuck on the end. So, you kind of just have to make a choice on how to use those shapes to come up with an approximation for this area. And the way that I'm going to do it is just use rectangles. I like rectangles because the formula for the area of a rectangle is very simple. It's just the height times the width. So let's approximate this area using rectangles. Well, there are lots of ways you could break this up into rectangles. You could maybe have one big rectangle down here, and then have another rectangle here, and maybe another rectangle here, and then wiggle one more rectangle in there, and then in there, and add the areas of all these rectangles together, and then you'd have an approximation. It wouldn't be exact because we're still missing tiny pieces of area here and there, but at least you'd have an approximation. Well, we could do it this way, but this isn't really a mechanical process. We couldn't sort of write down a formula that would work for any situation, because to decide where to put all of these rectangles, I've used the shape of this graph in a very important way, but not in a very mechanical way. We really want a mechanical way of doing this so that we can come up with a formula that works all the time. So let's back up. Let me redraw this picture. So I want the up and down to be a little more extreme. Okay, so we want a mechanical way to come up with rectangles to approximate this area. Once we have a bunch of rectangles, we'll just add all their areas together. So my idea for how to do this is, well, let's break this rectangle up, break this interval from A to B up into some pieces. Maybe, I don't know, 5 pieces. 1, 2, 3, 4, 5. These numbers that I'm writing down, they aren't x values. I'm just labeling the subintervals here. And then on each subinterval, let's just use a single rectangle to approximate the area in that subinterval. So in this first subinterval, we're going to have a rectangle that goes across the bottom, and then, well, we have to decide how high the rectangle is going to be. And that actually makes a difference. There are a few different ways to decide how tall your rectangle should be. You could always use the left-hand endpoint like this, in which case our rectangle would be that tall. You could always use the right-hand endpoint, in which case your rectangle would be this tall, a little bit taller. You could even use the midpoint like this, in which case your rectangle would be in between somehow. You can see that all of these different ways of choosing how tall the rectangle should be do give you a different approximation. So when we go to try to improve our approximation, we're going to have to ask ourselves, does it matter which one we started with? Just to pick one to start with, let's use right-hand endpoints. So I have reasons for choosing right-hand endpoints, which you might see later. But for now, let's use right-hand endpoints. Okay, for the next subinterval, interval 2, we're again going to go all the way across the bottom, and the height is going to be the height of the function at the right-hand endpoint. So that's like this. So there's our rectangle for the second interval, and then for the third interval, it's going to be something like this. And for the fourth interval, like this. and then for the fifth interval, like this. Okay, so the approximate area we get out of this is going to be, well, we said we're going to add up all of the areas of the individual rectangles, so that's going to be a sum. So I'll write sigma, and I is going to go from, well, our rectangle numbers go from 1 to 5, so from 1 to 5. And what we're adding up is just the area of rectangle number I. Okay, well, the area of a rectangle is the height times the width, so this is sum from I equals 1 to 5 of the height of rectangle number I. So I'll write height sub I to mean the height of the rectangle number I, times the width of rectangle number I. Well, if you look at all of these rectangles, if you assume that we've divided this interval up into equally sized pieces, then all of these widths are actually the same. So that would be sum from I equals 1 to 5 of height sub I times whatever this width is, assuming they're all the same, and we can insist that they all be the same. Well, we've broken the interval up from A to B. We've broken it into 5 different pieces. So this would be the width of the interval from A to B is B minus A. And we broke it up into 5 different pieces, so we should divide this by 5. So there's the width. Now for the height, well, the height does change, right? The height of each rectangle is different. But we need to come up with some way of expressing what that height is. Well, if you look at each rectangle, the height is determined by a certain point on the graph. Right? It was always the right-hand endpoint of the subinterval that gave us a point on the graph, and that's what we used for the height of the rectangle. So this height is the value of the function, but it's the value of a function at different x values. So there are different x values that go in here, and there's a different x value for every rectangle. So I'll put a rectangle number on here, right? So this spot right here, that's x sub 1. This spot right here, that's x sub 2. This spot right here, that's x sub 3, and so on for 4 and 5. All right. Now, I guess our final job for sort of finishing this idea is to express these x values in terms of all of the information that we started with, that is a and b and I. So how can we get to this x value? Well, look, we're starting at the left-hand end of this interval, and then we're moving over 1 step. And that gets you to x sub 1. To get to x sub 2, you start at the left-hand interval and you move over 2 steps. To get to x sub 3, you start at the left-hand interval and you move over 3 steps. So to get to x sub I, you start at the left-hand end of the interval, which is a, and then you move to the right, so add. How many steps? Well, the number of steps always matches the rectangle number here. So since we're writing down the ith x-coordinate, we need to multiply by I. And then we need to multiply that by the size of each step that we're taking. But the size of the step, that's the width of the rectangle. We already wrote that down. So that's b minus a over 5. So finally, this approximation is the sum from I equals 1 to 5 of f of x sub I, which is a plus I times b minus a over 5, times the width of the rectangle, which is b minus a over 5. Okay, that's the approximate area. Now this expression for the approximate area under the graph, this is called a Riemann sum. I think two ends. And it looks complicated, but remember, it's just writing down the area under the area of each rectangle that sits under the graph like this. So it's the sum of all the areas, so it's a sigma. This piece here is the height, and then this piece here is the width. So it's just the area of a rectangle.